Hi, everybody. This is Alex. Welcome back to the Astro Imaging channel. First day of March. We've got a good schedule coming up for you this March. We've been working really hard at getting people. Um, Eric was here last week. I had internet problems last week, so I couldn't get in. But Eric was here hosting, and he put out another broadcast for people to, hey, you guys out there, you need to volunteer and help do us some of these presentations so that we can share them with people. And Agapios heard us all the way over in Cyprus. I met Agapios 5 years ago. Whenever I go traveling, and I like to go traveling a lot, I always have a McFlurry at the local McDonald's in every country I go to. And one of the other things I like to do is try to go visit the astronomy shows and things, astronomy stores, just for something to do. And I met Agapios in Nicosia, and it is 4:31 in the morning right now, and he's been awake, astro imaging, taking pictures of planets, I suppose, and he's going to tell us about some of the things he's done. Before we do that, though, I've got to tell you some things about, well, about March. Agapios is here tonight. Gaston Baudet is coming here with us next Sunday night. I won't be here because I got to go to Cancun. My lovely wife is having her high school anniversary, their reunion down in Cancun. And so I'll be with the Golden Bears of Arlington High School in Columbus, Ohio, down in Cancun having a party. Maybe I'll be able to get in. Don't know. The week after that, we don't have anything planned yet. So remember what I was saying about we need you to volunteer? Please get in touch with us on the Astro Imaging channel. You can contact me on Cloudy Nights or Tolga. We're pretty easy to get a hold of, and get a hold of us and volunteer. The week after that, Deborah Saravelos is coming in, and she's going to be telling us about. Oh, I forgot to ask Tolga what she's going to be telling us about. And so I don't remember exactly what it is. The week after that is also not been scheduled yet, so we'll have to get a schedule on that. And then the next week is NEAF and NEAC. I want to tell you about NEAC. Bob Moore has been working really hard to plan a whole bunch of interesting sessions for beginning and intermediate and some advanced astro imagers. There's workshops at night. There's still room to sign up. I don't know about the hotel situation, but I know that you can still sign up for the conference itself. You get to come to the conference for a couple of days. You can sign up for the extra workshops in the evening, and there's some pretty good workshops going on. There's going to be dozens of vendors there coming into the room, and you can ask them questions, and it's really pretty interesting the level at which you can talk to these people and really try to work out some issues that you've been having, and where some things don't work, and they'll say, "Oh, have you tried such and so?" That's a pretty cool thing to do. So that's NEAC, and that's on Thursday and Friday of that weekend. And then, of course, Saturday and Sunday is the biggest astronomy show here on this continent, I think, and that would be the Northeast Astronomy Forum. And you're welcome to come. Lots of good speakers. Um, I don't know how many vendors there are, but they fill a gymnasium, if that's any indication, and it's a big gymnasium. So, so come on up. Okay, that's been New York and Suffer, New York, and you can go to the websites there to look up Astronomy Forum or Northeast Astro Imaging Conference (NEAC), and get them. Okay, I think I covered all the things I was supposed to make announcements of, but I think I was supposed to remind you one more time. We need volunteers. Some people ask me, what's it take to volunteer on this? Well, we hope you're articulate and we hope you can say stuff. But most of all, we hope that you really care about astroimaging and you've got something to share. And some people are sitting out there going, oh, but I don't know that much, man. I've just barely begun. I don't know if you realize it, but some of our most popular shows have been from people who have just begun. There are a lot of people out there just like you, and they want to hear it from your perspective as to some of the early things. Now, you don't have to be fancy, you don't have to know a lot, but you have to be able to say it. If you can make up a PowerPoint, or if you can make up a collection of slides put on a PDF or something like that. As far as the technology goes, a laptop with a webcam or a webcam on your desktop computer will actually do the job. It doesn't take much more than that. You're just sitting in a room and we're shooting the breeze. And then at some point, Toga goes, okay, everybody, we're going live. And then we have the presentation. So please, we need presenters. Now, on to Agapios. Agapios Elias comes to us from Nicosia. He's going to tell us a little bit about the island and his activities there, how they do it. And he's going to be telling us about planetary imaging with some pretty simple equipment. And I think it's about time for you to take it over, Agapios. So go ahead.
Okay, everybody. Hello from me as well. Thanks for having me. Let's see if I can share my screen here.
Okay, you're coming out okay.
How's
There
that?
you go. That's fine.
Okay.
And, Agapios, see down
Yeah.
on that bar across there, see where it
Yeah.
says hide? If
Yeah.
you press that
Okay.
hide button, there we go. That's out of the way. Now I'm going to
Okay.
click off.
Okay. So I'm here to talk about planetary imaging. My name is Agapios Ilia, and I live on the island of Cyprus. So Cyprus is a small island on the eastern corner of the Mediterranean Sea. And being on an island comes with everything that you would expect about living on an island. We have pretty much clear skies almost all of the time, apart from maybe a couple of short seasons of rain and a few episodes of Saharan dust. But most of the time, skies are clear. Skies are also pretty dark out here. So it's probably what you would expect as an ideal place to do astronomy. Now, being on the Mediterranean, that means we're also fairly low in latitude, and that has its positives, especially during the current age that we're going through, where the planets are mostly low in the sky for most of the northern hemisphere. And just to show you what I mean, here's a slide. This is what Jupiter will look like during the opposition date for this year. So we're going to get Jupiter at 33 degrees. Saturn will be at 34 degrees, fairly low, but not unusable. And Mars will come up to 60 degrees, which is a very welcome addition to the 30 degrees or so that we had Mars during the last apparition. So yeah, we get fairly good altitude for these low-lying planets. And here's what the island looks like. As you can see, most of the western part of the island is occupied by this rather large mountain. It's a 6.5 or so thousand-foot mountain. And we have another mountain range all across the northern shore of the island, a bit smaller, but still significant. And most of the main part of the island is basically flat. So I'm situated here, just on the northeastern part of the main mountain. The reason for all of this geography will be a bit more apparent later on. So let me just show you what I'm using. I have a Celestron 9.25 Schmidt-Cassegrain, a fairly well-known planetary imaging instrument. The reason why I prefer this instrument and why I think it's probably one of the ideal instruments for somebody to get into planetary imaging is because it's a fairly lightweight optical tube. It weighs about 9 kilos or 20 pounds. And this means that you can easily mount it and use it on a small mount, on a small equatorial mount. I started with Celestron CG5, and I've gone through a few mounts. I've had an EQ6, I've had maybe 2 or 3 different CG5s. I've tried an AVX, and now I've settled on the CGEM. And this just goes to the versatility of this instrument. You can also use it for deep sky imaging if you have a well-behaving mount and you know what you're doing with PhD and all that. You can get decent results in deep sky imaging as well with this. But for planetary, I think it excels. And it's fairly affordable and easy to put out really good results. So a few words about the accessories. I started out with a typical webcam, Philips SPC 900, a tiny 4mm chip, 640 by 480 pixels, and this would do about 10 frames per second uncompressed, and you could push it to 15 or 30 with compression. Soon after that, maybe a couple of years after I had the SPC, I upgraded to an imaging source DBK camera, which used pretty much the same sensor, but it could go up to 30 or 60 frames per second uncompressed. And I'm also using a Barlow lens. I still have my old Celestron Ultima, which I still use to this day, and a variety of filters and some other accessories. Here on the right, you can see the setup I was using back in 2009 or 10 when I first started getting into planetary imaging more intensively. This is probably about 5:30 in the morning. It's the summer, and I have Jupiter on the screen here, and you can see the webcam at the back of the telescope and some other stuff I was using at the time. I've since upgraded significantly. I've gone through a few different cameras, and I've settled now on the ASI 224 one-shot color camera. I tried monochrome as well. I had about 2 years with a monochrome camera, getting to learn how to do mono imaging and all that. And soon after that, ZWO came out with the 224, which is a really fast color camera. The manufacturer claims that it can do up to 500 frames per second, which is, to somebody who started out using a webcam doing 10 frames per second, 500 sounds like science fiction. I've been able to get up to 300 frames per second using this telescope with this camera. And the difference between what I was using before and this camera is just astonishing. It's really fast, really sensitive, and it gives out low noise data. Some other accessories I'm using now. I have a filter wheel with different filters, which we're going to take a closer look at later, and an atmospheric dispersion corrector. And out of all of the accessories that I've used, the one that has given me the most push further would be the atmospheric dispersion corrector. It's a small accessory, about as big as a Barlow lens, fairly economic to acquire, and it really helped push me further into getting even more detail out of my telescope. This is what the back of my telescope looks like currently. I have the camera here in the back. We have the atmospheric dispersion corrector over here. There's a Barlow lens somewhere between all of that and my focuser and the focus motor that I use to drive that focuser. I also use some other stuff like a Pocket Power Box to manage all the cables and the dew heaters and all that. But most of the attention on this presentation will be at the atmospheric dispersion corrector. So I've prepared some visuals. As we know, the atmosphere acts as a prism, so light coming into the atmosphere at an angle will get dispersed in its constituent colors. And what this accessory does is it basically cancels out that correction by inducing dispersion at the opposite direction. So if we take a look at the corrector itself, you'll see that it pretty much looks like a typical Barlow lens with the difference of these two levers sticking out the side. These levers run inside these channels, and there's a ring with a bubble level and a lock knob over here. You would attach your camera on one side, and you would attach the whole assembly in your telescope. So as I've said before, this corrector cancels out dispersion. And it does this by using two prisms. These prisms are somewhat wedge-shaped, and they're stacked on top of one another at their flat sides. So what you would do is you would rotate these prisms to achieve correction, to cancel out the effect. And if you see this picture here by John Boudreau, it clearly demonstrates just how much of an effect this corrector can have, and how much it can basically enhance the resolution that you're getting from your telescope. I mean, if you look at the left image over here without using the corrector, Mars is basically smeared with blues and oranges and pretty much very little detail coming through from the planet itself. Whereas over here, with the corrector set at proper correction, there's just so much more detail coming through. The fringes are almost completely gone and just details coming right through. So I've prepared this visual to demonstrate just how one would use this corrector. We have the images here from the manufacturer at the bottom right-hand side, and you can see the corrector at two different settings, at the original zero position or zero correction setting, and at the actual correction phase on the right. So if we take a look at the visual now, we can see in the center we have the back view, basically what you would see if you're sitting at your telescope looking up to the focuser. And at the left we have the side view, which would be what you're looking at if you're looking at off to the side. So I want you to concentrate your attention on these channels that we talked about before, where their levers run on these channels. And we should probably concentrate on where those two channels overlap. And if we find the central point of that overlap somewhere there, that's where our zero position is. That's where we want to set these levers. These levers are basically twist lock. You just twist them to loosen them up. You slide them around, and then you just tighten them again. So we want to line up those levers at the central point of that overlap and put the whole thing in the telescope. When we do that, we also want to adjust the levers so that they line up with the horizon, with the local horizon. And when we do that, we have zero correction. We're ready to begin correcting atmospheric dispersion. And looking at the screen, we're going to get the image of our target with that dispersion. It's important to note here that when these things first came out, some of them were assembled so that you would need to have them inserted in your telescope with the lever sticking out to the right. Some of them needed to have the lever sticking out to, on the left. And there's an easy way for you to determine, if you have one, just how you should have it inserted in your telescope. All you need is to just hold the actual prism in your hand at arm's length and look through at a horizontal reference line. And this can be a line drawn on your computer. It can be the side of your table or whatever is horizontal. And if you're looking at it and you start spreading your levers, what you want to see is you want to see that horizontal line going down. That means that your corrector is properly aligned, and you can attach it to your telescope and go ahead and do your imaging. So we have the corrector in the telescope, and we start spreading those levers. You want to spread the levers at equal distances from the center line, and keep looking at the target on your screen. And as you keep spreading those levers, you'll notice that dispersion is fading away, and that you're getting a slightly sharper view of your target. As you keep spreading those levers, when you have found the actual distance you want to be to achieve correction, you'll notice that dispersion is completely gone, and the live feed of the target is just so much more sharp and contrasty than it was before. And this is an effect that it's immediately obvious when you're looking at the live feed on your screen. And here, when you have found this position you want to be to achieve correction, that's when you would secure this rotating ring with the bubble level. If you were to keep spreading those levers, you would start overcorrecting, and you will notice that dispersion is now showing up in the opposite direction. If you remember before, we had the blues showing up on the left and the oranges showing up on the right. Now we're overcorrecting, so dispersion is coming up the other way around. And these levers actually have specific travel. So you may find that you've reached the end of that travel and you may not have enough correction ability. And what you can do here is you can increase the distance between your camera sensor and the corrector to gain back some of that correction. Now, it's important to state that correction can occur at any separation angle. This is dependent on what altitude your target is at the time you're imaging, as well as how exactly you have your optical train configured. Some people like to use the atmospheric dispersion corrector first. So they would have their focuser, their corrector, their Barlow lens, and then the camera, whereas some others like to have the corrector placed between the camera and the Barlow lens. And that's how most of the manufacturers suggest that you should use your corrector. That's how I use it as well. So depending on how you have things configured and how high your target is at the time you're doing your imaging, you'll find that the angle you need to set your levers at varies basically. So let's assume that we've set the corrector, we're imaging, everything looks good, and then some time has passed. And what happens here is over time, you'll notice that your optical tube basically rotates in relation to the horizon as it's tracking the object. So what's going to happen is you're going to start to lose your correction over time. And what you can do to address this is basically, if you remember these levers right on these channels, and there's some way to go on these channels. So you can readjust those levers, push them up again, and you will have restored your correction. Again, keeping that equal distances relative to the horizon line. So when you've readjusted those levers, you can then reset the rotating ring, keep the bubble in the center, and this will give you, again, some more time to keep doing your imaging. And you want to check this frequently. I typically check for focus and correction every about 20 minutes or so as I'm imaging. So having gone through the atmospheric dispersion corrector, having talked about the equipment and all of that, there's one other thing we want to consider when we want to do planetary imaging.
Could we
Yeah,
hold off on that for a minute? I think there
yeah.
might be some questions. Eric, have you been looking at the questions, particularly about the dispersion corrector?
Yeah, I think there's a lot of fascination with that. And I think you explained some of the variables on it. This is for a color camera exclusively, right? It's not if you're using filters.
Actually, no. You can use it for mono imaging as well. Obviously, this has an added difficulty factor because you can't actually see the dispersion when you're using a mono camera. So a lot of people like to set the dispersion corrector either visually or with a color camera. And then once they've adjusted for correction, they just swap out to their mono camera. Of course, mono imaging is far less susceptible to chromatic dispersion, but it still is. So yeah, you can use it for mono as well, and visual for that matter.
Do you know how much back focus it takes?
Again, this depends. Technically, you want to use roughly about the length of the adapter that comes with it. I mean, in this example, this is a ZWO corrector, and that extender on the backside is about 25, 30 millimeters. That's what I need to use at least to gain correction. If you extend that, you would extend that if your target was fairly low lying. Let's say for somebody living up in, I don't know, Canada or Russia or something, where they would get their planets at 10, 12, 15 degrees altitude, you may want to extend that. So it's not a strict specification. You don't need to use it with a specific back focus. You can vary the positioning of your camera to that corrector depending on how high your planets are.
Okay, how does temperature, seeing, affect these kinds of adjustments?
So temperature basically affects your focus, but seeing, if you have really bad seeing, you'll notice that it can be difficult to gauge when you're corrected. If you have obviously really good seeing, it's fairly easy. But I'm going to talk about a tool that you can use in FireCapture to set this corrector, and that will clarify things a bit further.
I think that's all. Yeah, FireCapture. I'm sure you're going to mention it. That is certainly a
Yeah,
piece of software
absolutely.
we all recommend. All right, I think
Yeah.
that's all for now.
Well, I think there's a couple. How much did you say this cost?
So this example from ZWO, I think currently it goes for about somewhere around $150, give or take. So it's fairly economic.
It doesn't change focus, right?
No, it does. It does.
It does change focus.
Yeah.
Okay, by the thickness of the prisms, or or what?
So
Just glass?
what happens here is typically you have your Barlow lens, then your camera, and you're focusing with that. When you swap out the camera to insert the dispersion corrector and reinsert your camera, you've gained some distance between that two. So focus will be off, and you need to readjust for your focus. And also, what's going to happen is, this is pretty important to mention, what's going to happen is if you're not using a telecentric Barlow lens, such as a PowerMate, what's going to happen is you're going to gain a lot of focal length. So it's going to throw off your focal length by a lot. In my case, without the corrector, with my 2x Barlow on the C925, I was imaging at about f22. With the corrector, I've shot up to f30. So it gives a lot of added focal length if you're not using a telecentric Barlow.
Okay, I think I asked the question wrong about the focus. If I've focused my planet and then I adjust the the dispersion, does the focus change?
You would think that the focus is changing, but actually you're losing the dispersion. So the view will be cleaner,
Yeah,
but
okay.
it's not necessarily from the focus. It's from losing all of that smearing you get from the
Okay.
dispersion.
So it's not as if I have to adjust dispersion, refocus, adjust some more, refocus. It's I adjust so that I've got a focused planet, and then I adjust my dispersion, and
Yeah.
I don't have to refocus. That's the question I meant to
Well,
ask in the first
well,
place.
you're going to refocus because you're looking at things so much more clearly. So
Okay.
you're actually going to refocus again.
Yeah. Yeah. Now
Uh,
you can see things more clearly to
yeah,
focus
yeah,
better.
yeah. You can see finer details. So then, yes, you would refocus again.
Is there a 2-inch version as well as a 1 1/4?
Not from what I know. I think there may be a 2-inch version, but it's from a premium manufacturer. So the price I mentioned before won't be valid. And it's good to note that in the past, dispersion correctors were fairly premium. I mean, I only know of a couple other examples that were around before the Chinese versions, and one was about $500, and the other was more than, I think, about 2,000 or something like that. So what these companies have done is they've made this accessory so much more affordable, and I think everybody who's doing any sort of planetary viewing or imaging, you ought to have one of these. And having
Is
used, yeah, go ahead.
is it of value in deep space imaging?
No, and the reason for this is because what you're doing is you're correcting for dispersion on axis. So off axis, things are pretty terrible. You're going to get a lot of aberrations from the dispersion corrector. I guess you could use it if you're only interested in a very tiny field around the center of your axis.
So
But
1 1/4. Well, it doesn't matter whether it's 2 inches, really. It's
yeah,
1 1/4 will do you.
yeah, absolutely, yeah, yeah.
Okay. Okay.
Okay, so to move on, um, everything we just talked about won't matter at all unless you have the seeing conditions working for you. So I'd like to talk a little bit about the seeing that I get here in Cyprus. I like to think of the atmosphere as a fluid body, sort of like looking down a swimming pool at the bottom of the swimming pool. When we have stable skies, basically what's happening is all of that fluid is calm and not moving so much. When we have bad seeing, what's happening is that uh, as you would expect, if you had people swimming in the pool, the body of water is just disturbed, so you're not getting any detail coming through. But what I also like to think of is that the swimming pool is just not one swimming pool. You have a lot of different layers of air above you, and what's happening is that they're not all behaving in the same way. You may have stable air in some layers, and you may have disturbed air in some other layers, and the wind speed and direction vary across all of these layers. So you may be getting wind coming from one direction in one layer and another direction in another layer and at different speeds. And then again, we're not always looking at the planets at zenith, where you have the least amount of dispersion and the least amount of disturbance from the atmosphere. We have the planets at an angle, so you need to take that into account as well. So for the atmospheric seeing, there's many different tools and websites that one can use to sort of get an idea of what to expect. And let me just show you an example. This is just one of the many different websites that I use to gauge the seeing. This is Meteo Blue, and this website has an astronomical seeing tool. Let me just pull up the prediction for today. I don't know if you can see that. Okay, can you see that?
Yes, we see it.
Okay, so on the left here, we have all these tools. We want to go to outdoor and sports, and we have an astronomical seeing prediction. So this is for now, for today. We have the clock here. We have 3 levels of cloud cover. We have a prediction of astronomical seeing that you can expect, and 2 different indexes of estimation of the seeing quality, the jet stream speed, bad layers, and the temperature, humidity on the ground, as well as what sort of celestial bodies you can observe. So if we look at this moment, it's 5:03, so we want to be looking at this row here. So what we can see here is that we have just a little bit of low-level clouds, no mid-level clouds, no high-level clouds. We can expect about one arcsecond seeing, and our seeing indexes are sort of good to average. We have somewhat fast jet stream speeds. We have 8 degrees outside, and it's 82% relative humidity. So what I want to show you is this prediction here. So by looking at this prediction, and I want to ask the guys here on the chat room, by looking at this prediction, what would you expect? Anybody?
I think we're contemplating it. I'm not quite sure. Why don't you explain again exactly how we read the chart?
Okay, so the first column is the clock. So we're looking at the time. The next 3 are clouds, low-level clouds, mid-level clouds, and high-level clouds. Then we go on to a prediction of the arcsecond seeing that we can expect. We have 2 different indexes. These basically go from 1 to 5, with 1 being the worst and 5 being the best. And we have 2 different indexes. Basically, they use 2 different models to forecast seeing here. We have the jet stream speed. The jet stream is basically the winds at roughly the 30,000 foot altitude. We have pad layers. Pad layers are essentially the layers of air where the temperature gradient is significant. And we have the temperature on the ground as well as the humidity on the ground. So by looking at this,
So you're saying we have sub-arc-second seeing, which would be
yes,
incredible.
yes,
Yes. It's a little warm out there today, but other than that, it looks like you've got like a 5's a 5. Doesn't the green column there summarize whatever else that says?
yes. So essentially, by looking at this, one would expect ideal conditions. Is that right?
Yes.
Okay.
So do you get sub-arc-second seeing where you are?
Yes, occasionally, yes, we do. But let me just talk about this view here. This was a 29th of May in 2019, and this prediction basically gave out the worst kind of seeing I ever had in this location. And let me just try and describe things. By looking at Jupiter, you would get a steady disk, so there wouldn't be any wobbliness. So Jupiter would look like it was steady, but there would be no visible detail inside the planet whatsoever. You would think that you're out of focus. You would think that you've lost your collimation. It would drive one mad, especially when you're up for how long and you're expecting to get excellent conditions based on a chart like this. And the reason for that, and the key here, is the last column over here, the relative humidity. See how the humidity is really low?
Mm-hmm.
So what this means for us, for Cyprus, whenever we have this prediction, we're getting warm, dry air coming off of the Saharan desert. And what's happening is we have steady air, we have still air, but we get a lot of Saharan dust. So we're covered in dust. And African dust basically completely destroys the images coming off of the telescope. They seem steady. The stars to a naked eye observer look like they're not shimmering at all. So one can be fooled into thinking that it's probably a good night to do planetary imaging. But once you train your telescope on the target, there's just nothing visible. There's no details whatsoever coming out of the disk. And yeah, as I said, this can be really deceiving. What I have found is that the best kind of seeing for my location occurs whenever we've had some dust storms, some thunderstorms, whenever we have a lot of humidity all around. Say a night where your dew heaters can't keep up, it's just so humid, everything is dripping wet. That's when we get the best kind of seeing. So to talk a little bit about the seeing again here, I have this visual from Damien Peach that you can see here, where we can see how the airflow is affected by the mountains. So I'm located here in the yellow dot, in basically the center of the island, just off to the side of the main mountain over here. So whenever I get the winds coming from, say, the northwest or the southeast, that's when good seeing occurs for my location. Whenever winds are coming from the north, for example, or the west over the mountain, that's when things get really turbulent. And even though my general prediction may be for good seeing, my actual seeing greatly depends on from where the wind is coming from. Again, if you take a look at the graph over here, we have winds coming from the left side of the screen. If you're situated before the mountains, you're going to get good seeing. If you're situated after the mountain range, you're going to get all of the junk, all of the turbulent airflow, and your views will be completely destroyed. And yeah, as I said, this is really the key to planetary imaging. You want to keep looking at where the wind is coming from what direction, not necessarily from what speed. The speed of the wind doesn't really matter. I've had good seeing with fast wind speeds, and I've had really bad seeing with no wind speed. So the speed doesn't really matter, at least for my location. What matters is where that wind is coming from, and across all the layers, from the surface layer all the way up to the outer layers in the atmosphere. So this is just another visual where I can show you how things behave. For my location, if I have the winds coming from the northwest, basically from this gap between the mountains across this flat spot on the island, that's when I get my good seeing, my better seeing. And what you want to look at again is, if you imagine that wind is basically distributed across layers from the surface all the way up to the outer edges of the atmosphere, what you want is you want to have a way to look at the wind speeds across all of those layers, wind speeds and directions. And what you want to have is all of those layers sort of coming from either the same direction or spread across, say, one quadrant. So if you have winds coming from the north and the northwest and the west, even if their speeds vary, the fact that they're coming to you from more or less the same direction, that's what's going to give you better conditions. But if you have layers of wind sort of overlapping and crushing into each other, that's when seeing would be bad. This is what I've found to be true. And again, the speed of those winds doesn't really matter. What matters is their direction. I've had good seeing with no wind, with wind, and with a lot of wind. As long as those winds are coming from more or less the same direction, that's when things are really good for planetary imaging. And that's when typically we also have humidity all over the air, and things are stable enough to get good images of the planets. So if we don't have any questions on the seeing, we can go further into some software I want to show you.
Sure, go ahead.
Okay. So to capture images, I use a multi-step process. We're going to go through collimation, acquisition, alignment and stacking, stretching and sharpening, derotation, and final touch-ups, cosmetic corrections in Photoshop. And this is the software that I'm going to show you. And this process is going to jump back and forth a couple of times. We're going to start things with collimation. We're going to move on to acquisition. We're going to go through alignment and stacking. Then we're going to go to stretching and sharpening. Then we're going to go back to alignment and stacking, back to stretching and sharpening. Then we're going to move on to derotation. Then we're going to go back again to stretching and sharpening. And then we're going to finish up with our cosmetic corrections. We're going to follow sort of a double retrograde processing method. And the reason for this is going to become apparent further on. So to begin, we're going to start with collimation. As we know, collimation basically is the process of aligning the optics of your telescope to ensure you're getting the best possible images that your instrument can give you. And there's many different methods for collimation. There's the visual method, there's tools that you can use, there's accessories that you can use. and I've gone through all of them, every single one of them. I've spent many days, many nights investigating all of these methods to try and find the one that works best for me. I've tried naked eye collimation, being on your knees, looking up through the focuser tube and getting up, adjusting things, and then going back down. I've used most of the tools that are out there for collimation, such as artificial stars and whatnot. And what I have found to be the absolute best tool, at least for me, is this software called MetaGuide. So MetaGuide is originally a guiding software, sort of an alternative to PhD. And you can see the link here from where one can download this software. And what this software does differently is that it's giving you a detailed view of the airy disk, even in bad seeing. And it does this by using video feed. So it's getting your images from your camera. And if you give it your specs, if you give it your instrument specifications, what sort of aperture you're using, what magnification you're using, what kind of camera you're using, it can calculate what to expect from your telescope, and it gives you a live view of the behavior of the airy disk, and it gives you this graph. Basically, you can see this green circle in the center, which is basically your star. You can see the airy disk coming in and out of view, and you can see a red dot in the center sort of bouncing around. But it's bouncing around, and if we assume that we're miscollimated, you're going to see that that dot is bouncing around, but it's showing some kind of preference. Can you see it?
Mm-hmm.
Can you see that there's a preference?
Yes.
Okay, so that's giving us an indication that we're miscollimated. So what we want to do is we want to adjust our collimation in a way that we're pushing the star towards where that dot is. And what the software can also do is, I mean, obviously, if you twist your knobs, you're going to throw off your the target from the center of your screen. So what this software can do is it can also talk to your mount, and it can reposition the star back in the center of the view every time you're adjusting things. So it just makes everything so easy for you. So what you want to do, what you want to accomplish, is to get that dot to more or less hover without showing any kind of preference. And another tool that you can use is the full width half maximum reading that you're going to get over here. So the software will tell you what you can expect from your system. I mean, for me here, I can expect a 0.588, but the actual view that you're getting because of the seeing will be different. But as you're adjusting, this number is going to go down. So you want to get this number as low as you can, and this will vary from night to night, of course. You want to get that number as low as you can, and you're going to notice that the dot here will hover more or less over the green circle, which is a star, and you want to have no preference visible. Once you've achieved that, you can then save a screen capture from the software, and you can enhance the view here, and you can see how the airy disk shows up nicely, uniform all around the star, and that's when you know that you're collimated. And I've been using this for 10 years now, since 2010, and I can tell you that it may look daunting, as any software looks whenever we're just freshly going into it. But once you get your head around how this works, it's an indispensable tool for anybody who wants to do any high resolution planetary imaging. And you can help things a bit by using a red filter. I use a 610 nanometer filter to just basically peer into the near infrared a bit better, where things are usually a bit calmer when it comes to the seeing. And you want to use a bright star, but not too bright. And you don't want to be saturating the view here. If we go back here, if you're saturating the view, you're going to get a red line show up on the top. And what you can do is you can go into your settings and drop down the gain or the exposure so that you're at a point just before that red saturation line appears. So yeah, as I said, I find it to be indispensable. I start with this every time just to make sure that everything is collimated and lined up. The telescope is almost always ready to be used. I keep the telescope outside in a shed, so it's always set up, always balanced. I just stick in the camera and go. But I roll it, it's on wheelie bars, so it rolls from the shed out to the observing spot. And even that small disturbance that happens from rolling the telescope just a few meters results in miscollimation. So I always load this up first to check my collimation and then go on to acquisition. Typically, I would collimate well ahead of time. Let's say that my planet transits at 4 in the morning. I'm going to be collimating early on at night to get things fairly close to where they want to be. And then I'm going to check again just before I'm ready to start getting data, just to make sure that everything is where it should be. So moving on to acquisition. The tool of choice here is, of course, Firecapture. And coming from, back in the day with webcams, we used to have to use 2 different software just to run the imaging camera. I don't know if anybody remembers, but back in the days of the webcam, we had one software to run all of the parameters, the gain, the exposure, the file size, and another software to look at the live feed. Now with Firecapture, basically Firecapture is almost a one-stop shop. It can run your camera, it can talk to your mount, it can talk to almost all of your accessories, and it just makes life so much easy for planetary imaging. So here's a view here that I pulled off of Firecapture, and I could spend a lot of time going through all of the different modules, all of the different settings, but I'm just going to talk about the basics. And the basics are essentially the gain, the exposure, the frame size that we're using, the histogram. And before we even go into all of these, we want to make sure that we're using WinJuPos file naming. And this again will become more apparent further down this presentation, but we want to be sure we've clicked on WinJuPos file naming. This will make our life easier further down. So what I like to do with Firecapture is use the auto run feature. The auto run feature is basically a feature that allows you to capture many files, many video files. And what I do is after I've done my collimation, I've adjusted my dispersion corrector, and I'm ready to go, I'm not just going to sit there and wait for when I think that the seeing looks better to click capture. What I'm doing is I'm setting up a series of captures, maybe 10, maybe 20, maybe 30. What I want to have is a long extended duration of time where I'm capturing videos one after the other. And the reason for this is, at least in my case, the seeing here is never consistent enough to allow somebody to just sit there and look at the screen and sort of gauge when things look better and click play and get whatever data you need to get. What's happening is, even if the predictions speak of good seeing, what's going to happen here is you're not going to have good seeing all the time, all night. You're going to have fair seeing, bad seeing, a couple of bursts of good seeing, maybe a short burst of excellent seeing, and then back to extended periods of good or fair or bad. And it just basically, everything just shifts around all the time. So what I do is I set my auto run and I just let the thing work for me, have it capture continuous videos one after the other. And you can see here in this example, I have two images here, two different views with just a minute apart, and you can see the difference between the two. So I end up with a large collection of video files. I like to shoot for about a 2-hour period centered around when the planet is highest in the sky. So if, for example, Jupiter would transit at midnight, I would typically start shooting at 11 and then go all the way to 1 in the morning, or even longer, depending on what's going on. If there's like a satellite transit or a shadow transit, and I want to capture the whole thing, I may actually go longer, but that's what I would do typically. So with fire capture, what I like to do is I like to set things up so that I'm getting the most frames per second possible, with keeping a good histogram exposure, preferably by using less gain. So we balance gain with exposure to fill our histogram, but what we want to do is we want to keep the FPS as high as possible by using the least amount of gain that we can, because gain is basically it's going to give us a brighter image, but it's also going to introduce more noise into our individual frames. So typically for Jupiter, let's say with my system, I can do somewhere around 200 frames per second, maybe a bit less, maybe a bit more. With Saturn, I can probably do about 100. And with Mars, I can maybe shoot for 300 frames per second. That's all depending on the night and how good the seeing is on each night.
Agapio?
Yeah.
Can you comment on the size of the files that you'll generate with that kind of shooting?
Oh, absolutely. Yes. So typically, if I'm shooting for, let's say, a 2-hour window, I will end up with roughly about 300 gigabytes. If I have more than one target per night, one example is last year, I think we had Mars and Jupiter and Saturn sort of trailing each other in the night sky. And I ended up with about 700 gigabytes of data for just one night. So one can expect a lot of data, really large data files coming out of this process. But there's ways to basically mitigate that. And one example is by using the region of interest feature in fire capture. So if you imagine that your sensor, let's say in my case, the ASI 224, it's a 1300 by 900 pixel sensor. But when I'm shooting through my telescope, I'm not using all of that. I'm not getting Jupiter across the whole sensor. I'm getting the small central part of that sensor. So what you can do with region of interest is basically ignore the dead space, all of that blackness that's around your target, and this will help you getting smaller file sizes, but also it can boost your FPS, your read speed from the camera. And another thing, Firecapture can talk to your mount. So you can set up Firecapture to auto guide in a way, basically nudge the planet around so that it's always in the center. You can fine tune it to make sure you're always looking at the planet. You don't have the planet trailing off. So if you use auto guiding and region of interest, you can basically trim down your region of interest so that it's just letting just a little bit of that space and really increase your frames per second. Another thing, and this will go towards focusing. Firecapture has this tool, the auto align tool, which basically what it does is, if you imagine we're outside at the telescope and we have our planet, what you're looking at is the view will be shaking slightly. So the planet will be wobbling slightly left and right, or a lot if it's windy. So what auto align can do is it can basically center those frames coming in from the camera on the planet. And when you click on it, you'll see that the target will be frozen in the center of the screen, and you can then focus your telescope, and the effect of you touching it won't show up in the frames. So this will greatly help somebody who's, let's say you're trying to focus at 4 a.m. and you're touching your telescope, and you're not going to get that shakiness. Everything will be frozen on the screen, and it will make you think that you have the world's greatest focuser. So that really helps as well. And I know a lot of people who keep that on when they're recording so that their planet doesn't show up in different positions throughout the individual subframes. You can also do that if you'd like. And there's many other features in Firecapture. You can have it talk to your filter wheel, focusers. You can set different filter offsets. You can set different filter parameters. So you can, for example, somebody who's doing mono imaging, you can use profiles in Firecapture. So you can tell it that, with this system, with the blue filter on Jupiter, I want to be using a 600 by 400 frame. I want to be using this amount of gain. I want to be using this kind of exposure. And you can set that for each and every different filter that you're using, so that when you're going through those filters at the time of capture, you don't have to adjust things at that time. They're already pre-adjusted. Or at least you can be pretty close to where you want to be for the night. So going back to my process, by using AutoRun, I end up with a large collection of files. And the reason for this is, as I said before, for me, for my case, the seeing is never consistent. So most of the best images that I've ever had didn't happen when I was there looking at the screen. They happened because Firecapture, by using AutoRun, sort of kept recording even though I wasn't looking at the screen, and it caught those instances of better seeing. Another tool that's really handy with the atmospheric dispersion corrector is the ADC adjustment tool in Firecapture. And this tool is really ingenious. What it does is, by looking at the live feed coming from your telescope, it will show you this graph, this red and blue circles and the white circle. And what you want to do when you're adjusting your atmospheric dispersion corrector is you can try boosting the gain or the exposure at that time to sort of saturate the colors even more. And what you can do by nudging those levers and looking at this tool is you're going to see the red and blue circles bounce around the screen. And as you're adjusting, you're going to see them start getting closer to the white circle. So what you want to achieve is a good overlap between those two and the white circle, but you also want to put everything as close to the center as possible. So when you're adjusting the corrector, uh, the planet will shift up or down in the screen. So whenever you're adjusting, you want to recenter your planet and then adjust again and again and again until you have the planet centered in your sensor, and you have these overlaps almost completely covering each other. That's when you know that your corrector is where it should be for proper correction. And of course, when you dial back down your gain and your exposure, you'll see that the view is noticeably sharper. And of course, you don't have any chromatic dispersion.
Agapios, do you want to
Yeah.
mention the cost of
Sorry, I didn't hear that.
the cost of all this software? This is all free software you're going to mention, right?
Yeah. Every single software except for Photoshop is free.
Which format do you use to capture? On the top, it has 16-bit, and there's 8-bit.
You mean file capture?
Yes. Yes.
Okay, so when you're using a camera such as the 224 with file capture, you can choose to use 8 or 10-bit or 12-bit. For planetary imaging, I use the lower bit setting, and this also boosts the available FPS that you can get from your system. And of course, because you're stacking many thousands of frames, you're not really losing any of that fidelity. So yeah, for this kind of imaging, I use the lowest setting, and as I said, it just boosts the available FPS even further.
There's also a question.
Yeah.
If the corrector and software help with higher latitudes.
Okay, so the corrector can help you no matter what latitude you are, or no matter how high the planets are for you. It can help you if you have really low-lying planets, 10, 15, 20 degrees. In my case, roughly 30 degrees. It can even help you if the planets are at 60 degrees. Dispersion is happening across the entire sky. It's obviously less at zenith, much less, but as you start to climb down from zenith, dispersion occurs, and it just increases by lower altitude, but it can help you no matter what. Some say that you only really need to use a dispersion corrector if you have your targets below 60 degrees. Some say you can use it for further. This will be the first year where I'll be using the corrector for high altitudes. I'm going to get Mars at 60 degrees this coming apparition, so I'll have a much better idea of how much the corrector will help at that altitude. I've only had the planets in about 30 degrees for the past 5 years. So ever since I started using the corrector. So they've always been roughly 30 degrees for me, and I can see a huge improvement at 30 degrees. This will be the first year where I'm going to have sort of a higher altitude planet, so I'll have a better idea further down. But I'm thinking that yeah, it can definitely help no matter what the altitude is.
Okay. Let's see. Where are we? Hangouts. Okay. It looks like you're about to go into how to process and derotate and a few other things. You know what? I know I told you before you started that we don't really have a time limit on this, but I think with all the questions we've been asking you and all your cool stuff about that ADS, We took a lot more time. Is it possible to invite you back sometime in the near future where you could continue this
Yeah,
discussion?
yeah, absolutely, absolutely, yeah.
Hey, um, I would suggest that everybody type in your questions about collimation, acquisition, alignment, and stacking. All the stuff that Agapios has done so far. Type them in, get them in there right now, and we'll continue to visit with Agapios. Agapios, could you? I think we talked about you. Tell us about your website a little.
Yeah,
Could
yeah.
you jump up to that, and then we're gonna schedule you March 15th. Sound good? Or you want more time? Or we can do it offline and get back to you about
Yeah,
when we're back. Okay, but tell us
absolutely, yeah.
about your website and what else you got going. Eh?
Okay, so my website is here, and you can log in and check out what I've been doing for the past years. I mainly do solar system imaging. The planets, of course, are what interests me the most. I have a few other examples, only a little bit of deep sky, some phenomena, mostly the planets. And you can log in and check out some results. If we have time, I just wanted to quickly mention one other thing that I find is probably the best reason to use a color camera.
Okay,
Just quickly.
hang on a second. Hang on. I want to be clear. First off, yes, I am broadcasting. Okay. Yeah, we've got time. We just don't have time to do all the stuff that you've got
Okay.
for us.
Okay.
Okay. So
Okay.
I think that we could have gone on till like 10:30 tonight if 10:30 California time. I don't know about you guys back east. So, and I mean, the sun's going to come up pretty soon. You're
Yeah.
an astronomer. Can you handle anyway? Go on. Take it.
Okay, so I just wanted to skip over all of this and just go into some examples that I have here. And I wanted to show you probably the coolest reason why one would want to use a color camera and my method of shooting for large windows of time. You can end up with some really interesting animations that you can easily compile from all of that data that you captured. I have an example here. I caught a double satellite and shadow transit on Jupiter. And if you take a look at my notes here, this was April 1st, 2016. And I mentioned that it was a marathon night with very variable seeing conditions. And you can see those conditions change in the individual frames of this animation. This is a 140 frame animation. So I got 140, or I kept 140 files, which I processed identically and then compiled into this animation. And this yielded 393 gigabytes of data. And that's roughly, 4 hours. So yeah, one can expect massive data files coming your way if you're doing this kind of imaging. And another example, I also caught an eclipse of Io. You can see the moon Io here, sort of hiding behind Jupiter in its shadow. And later on, when I process the individual frames, you can see how Io sort of lost its color and its brightness gradually. And the last frame here, you can see Io partially obscured by the shadow. And this is all really easy to do, to compile these kind of animations if you're doing this sequential imaging that it looks like we're going to have to talk about at another session.
Yeah, that's cool.
I have a question about data acquisition.
Yeah, go ahead.
So with these large files, I'm assuming you're not recording onto a solid state drive, which I thought was going to be necessary to get the frame rates you get. Are you able to get those frame rates recording onto a regular hard drive, or do you just have a really beefy solid state?
The system I'm using now has a solid state as well as a fast, typical hard drive. But I would highly recommend that you use at least a 7200 RPM regular hard drive, or if you have a large solid state, that's even better. But no, you can get these speeds with a regular hard drive, at least a 7200 RPM one.
You record directly onto the regular hard drive.
The system I'm using now, it's a dual hard drive laptop. So I'm recording, I have a 1 terabyte 7200 RPM as my data bank, and 256 solid state for everything else. So yeah, I record directly on the 7200 and I'm still getting these speeds.
Okay, good to know. Thanks.
Okay, so what should we do? Should we?
Well, what we're gonna do is we're gonna put a bookmark on your program, and
Okay.
we're gonna bring you back. We'll offline. Um, well, after Tolga takes us out, we'll stay in the room and we'll discuss a good time for you to come back. But I can tell by the comments that people are making over there that they want you back. They've got several
Okay.
commented that this has been a real good, real informative show. Lots of comments about you've told them things that they didn't know. Look, I've done this stuff before, and I've watched these shows before, not just the Astro Imaging Channel, but at NEAC, at the Advanced Imaging Conference. I've seen people. I've seen Damian Peach. I've seen Christopher Go, and I learned some stuff tonight that I didn't hear from them. And you haven't even had a chance because I talked too long because everybody asked these cool questions. You haven't even have a chance to show the rest of the magic that you can do. So we're
Yeah,
going to
there's a lot of stuff that we haven't even scratched the surface yet.
okay. It would be unfair to keep everybody awake because they're all astronomers. They need their sleep, and because it's almost daylight over there. So anyway, you kept your audience there. We got 59. I think at one point we had 60, but otherwise you kept your audience the whole time. And we're about to say good night. I think we got all the questions here. You guys know that we'll be back. Keep watching. And remember, we need those volunteers. We need you guys to come through. Agapios did it. And I don't know many of us could match Agapio's skill in the presentation tonight, but that's not the point. We can all help each other in a lot of different ways. So if you can do it, or if you know somebody, if you've seen some good presentations in your club level, local star parties or something like that, hook us up with them. We need presenters. The hardest part of putting this show on once a week is getting people to present. We really need the help doing that. So please do your share. Having said that, take us out, Tolga.
All right. Good night, everybody. See you next week.